Every API you've ever built or called has one absolute requirement before it does anything else: answering the question, "Are you allowed in here?" That's authentication. It's a bouncer checking IDs at the door. But there isn't one correct bouncer to hire. There are 6 popular ones, and each is built for a completely different kind of club. Hire the wrong one, and the stakes are steep. Using a simple method for a public app can leave user passwords readable in plain text, while implementing a complex system for a small internal tool adds months of unnecessary engineering overhead. As we look at these 6 methods, you'll see they handle information in 2 distinct ways. Some require the server to remember every visitor, while others allow the server to remain oblivious. This choice dictates how easily you can revoke access later, and how many thousands of users your system can handle at once. Let's walk the strip. We'll map all 6 methods, strip away the jargon, and find the exact scenarios where each thrives or fails. Effective API security requires matching the strict limitations of a protocol to the specific constraints and budget of your application. This chart graphs our options by implementation complexity on the bottom axis, and security and scalability on the side. Down here in the bottom left, we have stop 1, basic auth. Think of this as the megaphone. You take a username and password, glue them together with a colon, encode them, and shove them into an HTTP header. The problem is that the base64 encoding it uses is not encryption. Anyone intercepting that request can decode it to plain text in seconds. Without HTTPS wrapping the whole conversation, your password is just traveling out in the open. Moving slightly up and to the right, we had stop 2, API keys. This is the VIP wristband. It's a long, random string issued once and attached to every subsequent request, allowing seamless machine-to-machine communication without constant logins. But wristbands only work if they can't be easily duplicated. If you bake an API key into a mobile app or public JavaScript, attackers can easily extract it. It's exactly like printing your VIP wristband on a t-shirt for anyone to screenshot. Both basic auth and API keys are effective for internal tools, quick scripts, or secure server-to-server calls, but they create significant security risks if exposed directly to the public internet. When we move to public web applications, we arrive at stop 3, sessions and cookies. Think of this like checking into a hotel at the front desk. This diagram shows the mechanics. You log in, the server files a session record in its database, and it hands your browser a random cookie. On every future request, your browser flashes that cookie, and the server looks up your record to see if you're still checked in. The HTTP-only flag provides a vital layer of protection here. It locks that cookie away from the browser's JavaScript. Even if an attacker sneaks malicious cross-site scripting onto your page, they still can't steal the token. But there is a heavy tax for this security. Sessions are stateful. The server has to remember you. If your app grows and spans across dozens of servers, they all have to constantly sync with that central database to agree on who is logged in, creating technical bottlenecks. Session-based auth is ideal for monolithic apps, where you might need to instantly revoke access and kick a bad actor out. However, it becomes difficult to manage for systems that demand infinite horizontal scaling. When that hotel becomes a sprawling international airline alliance, you need a different bouncer. Enter stop 4. JSON Web Tokens, or JWTs. This is the tamper-proof passport. A JWT is broken down into 3 chunks: a header, a payload containing things like your user ID and role, and a cryptographic signature. All of this information travels directly with the client. This allows for high scalability. Because the server can mathematically verify that signature on the spot, it doesn't need to do a database lookup on every single request. It's stateless, letting it move across sprawling microservices. But there's a trade-off: the stateless illusion. Since the server has no memory of the token, revoking a user's access before that token naturally expires requires you to build a block list. Now every server has to check that block list on every request, reintroducing the exact same bottleneck we were trying to avoid. JWTs are an effective tool for distributed networks that need scale, but you trade away the ability to easily perform instant access revocation. Now, what if the payload isn't a profile picture update, but a $10,000 bank transfer? You need stop 5, HMAC. Think of this as a medieval wax-sealed letter. HMAC takes a payload and hashes it with a shared secret, a unique identifier, and a strict timestamp. This mathematical seal proves that the data hasn't been altered by even a single byte in transit. It provides protection against replay attacks. But it is unforgiving. A single formatting deviation or a clock drifting by a few seconds breaks the entire system. Finally, we reach stop 6, OAuth 2.0. When you pull up to a restaurant, you don't give the valet your house keys and safe combination. You hand them a valet key that only starts the car. This animation shows the protocol in action. Instead of giving a third-party app your password, you are redirected to a dedicated authorization server, like Google. You approve a limited scope, and Google hands the app a short-lived access token. The advantage here is that the third-party app never sees your credentials. It cannot leak what it never had, removing a major security liability. HMAC and OAuth 2.0 provide the highest level of tamper-proofing and secure delegation. They require dedicated authorization servers and complex cryptographic signatures, tools that are necessary for bank-level transfers, but often add more overhead than a simple project needs. We have our 6 bouncers, but when you are starting a brand new project, how do you know exactly which one to hire? Look at this decision tree. The very first split dictates your path. Are you building for internal tools, or is this a public-facing system? If it's internal, you can move fast. Use basic Auth for quick internal dashboards behind a VPN, and use API keys for private server-to-server machine communication. On the public side, if you are processing financial webhooks where payload tampering is a zero-tolerance event, you route straight to HMAC. For standard web apps, your choice depends on your architecture. Choose sessions for monolithic single servers, where you need the power to instantly kick bad actors out. Choose JWTs if you are building microservice networks that require raw, stateless scale. And finally, reserve the complexity of OAuth 2.0 for when you need users to sign in with Google or grant third-party calendar access. Choose your authentication protocol by matching the strict limits of the protocol to the exact building you are trying to protect.